Great. So today we're going to start, we're going to kick off these examples of regulatory dynamics set. And we're starting with something rather interesting example that occurs, and it's still a big element of research nowadays, which is what happens after transcription, right? So let's go back to our model that we use for when we are generating proteins in the system. So first off, we have DNA, which is transcription into mRNA, but after that, we have mRNA that it's like floating out of the nucleus, going to the ribosome, right? And the different elements that are concerning all of there. So here we have a depiction of that. This is mRNA that it's now being interpreted, right, through the tRNA, etc., and it's producing protein synthesis. However, there is something that it's oftentimes called microRNA or sometimes small RNA or silencing RNAs. That goes with different names, and there's a huge variety of them too. But here we're going to try to synthesize all of this in a very simple model that is going to give us a sketch of how we can deal with this, post-transcriptional regulation. What does this microRNA do, right? Well, it can do multiple functions, but one of the functions that it's been observed is that it regulates the mRNA that's been expressed. So you generate mRNA, right? And then you also generate a certain amount of sRNA. Now we're going to call this microRNA, or small RNA, to distinguish it from the messenger RNA, we're going to call it sRNA, okay? So in our system, we're going to have some sRNA, we're going to have some mRNA, and what happens is that this sRNA can bind into the mRNA and therefore sequester it and not allow it to be read. Yeah? Somehow this inhibits the expression of this particular strand or this particular part of the genome, right? Okay, so this is the picture. This is a very general picture. Here I'm skipping a lot of details, and this is just a very simple model that allows us to probe and understand how these dynamics, this is a regulatory dynamics, because after all, regulating the expression of this messenger RNA, we're going to focus on seeing how dynamically can this be modeled, all right? So we have now our picture here. We have mRNA, we have sRNA, and these two can bind together and therefore prevent this mRNA to be expressed. How do we depict this model, right? Can we actually do one of these nice pictures that allows us to maybe go to the next page and develop some ordinary differential equations? Well, we can, right? So we have a population of mRNA in our system. Great. We do also have, depending on the genome that we are studying, I'll give you some examples at the end. We could have some sRNA that is also being generated. And what's going on is that this is going to be generated at some particular rate, right? So we say that this is being generated just at some particular rate alpha, and this is being generated at some particular rate mu. So they are just being pushed into the system. They are introduced into the system at this rate. However, what is important is that there are two important facts about mRNA and sRNA. Both of them decay, right? So we are going to say that this mRNA is going to decay at rate delta. They do not decay at the same rate precisely because their lengths are so different, and as a matter of fact, sRNA tends to be less stable than mRNA. So we're going to say that they do decay at two different rates. One is going to be this delta, and the other is like capital delta, right? Both are decaying, but then the most important, crucial aspect of this model is that one can somehow capture the other, sequester it, and therefore rendering useless. In a sense, we are going to be focused on what's the concentration of free mRNA, which is the one that's going to be, after all, expressed, right, as a protein. Well, therefore, we need to somehow invoke an interaction here between these two that basically it kind of provokes this binding, right, between mRNA and sRNA, which is, if you want, another sector of the population, but really it just keeps there and never does come back. So this is a one-directional arrow, right? And we're going to say that this is happening at rate gamma. So now we have our picture, right, that allows us to define our ordinary differential equations, and from which we can start working with our tools. And this is a very, very simplified mapping, but somehow yet it'll give us some very good intuition on how can this evolve dynamically. In order to make things a little bit easier, let's say that m of t, this is a variable that I'm just invoking now, it's going to be the concentration of mRNA, just for simplicity of notation, mRNA over time, okay? And then, for example, S of t is going to be the concentration of sRNA over time. Notice that both these concentrations are free mRNA over time, free sRNA over time. As soon as they get locked in, we actually do not care about them anymore, okay? Great. Well, with all of this, oh, by the way, also, let me say something. Not only mRNA decays, but also it can be it's translated as well, right? So mRNA also comes into the ribosome and then it's translated, and when it does so, it's kind of like we're putting everything in here. Both it decays, but also if it's translated, well, we are already expressing it, so the regulatory aspect that it's brought by the small RNA, it's no longer functioning, right? So if you want, you could say that delta is related to 1 over tau, where tau is the translational timescale, right? So this would be the translational timescale. Okay? So that also is introduced in this model in a very approximated way, but it still will work and give us some interesting responses. Okay, how do we now go on to our beloved ordinary differential equation system that captures all of these? Well, now we have defined the variables, so we can work with them rather more easily. And first off, we want to focus our attention on how the concentration of mRNA is evolving over time. Well, as I said, mRNA is introduced into the system at rate mu, right? But mRNA interacts with sRNA. There's an interaction here, which is governed with, by this coupling gamma. And this interaction is inhibitory, right? Because once they're bound, this is sequestered and it no longer can be expressed. So there's going to be a minus sign here. And this is the coupling between the mRNA and the sRNA. But finally also, mRNA will either be expressed or translated, or will be decaying. So we are going to pull everything here together with this parameter delta. Great. Now, if we look at the equations for the sRNA in the system, they look pretty much similar. Alpha is the introduction rate, right? The sequestering interaction is going to work symmetrically. They are both being sequestered here. So we're going to have the same term. I mean, if you want to be a little bit more sophisticated, you could say, well, maybe there's multiple sRNAs that are binding into the mRNA, and therefore this constant here should be a different constant, yada, yada, yada. You can do that, and I encourage you to explore this. But for the purpose of this simple exercise, I wanted to reduce this way. Great. There's also the decay rate, which is different, as we notice that this is not an increment of s, this is big delta times s, okay? And now we have all the equations that I want to deal with. And there's now, after this, a very important assumption that we are taking, which is the following. Because sRNA is a much smaller molecule and it decays faster, right? We could argue that this equation, the second one, is going to equilibrate very rapidly. We've seen other examples that we explore or we kind of push this way. So we will assume rapid equilibration or rapid equilibrium for S of t, right? So in other words, we're looking at a time scale that it's the time scale governed by the either translation of mRNA, or if you want, translation and decay of mRNA. So this is the time scale that we're going to be focusing on, and we can argue that this time scale is much larger than this one, therefore this should be in equilibrium. Well, this gives us the following, right? So we can say that we are basically working at a time scale such that, right? So our time scale, if you want, is such that this is basically 0, or if you want, approximately 0. Great. And from here we can say that there's going to be an equilibrium value of sRNA, right? And basically this is setting this equals to 0, which gives rise to this expression here. Great. Notice that we have the concentration of mRNA here as a variable. That will come and kick us back, right? Because as soon as I substitute the effective concentration of sRNA in the system over here in my first equation, then I'll see an M in the denominator, and I'll have to deal with that. And we will deal with that. Indeed, now I bring this onto my equation that I had here, right? I bring it back, and what I get is this funny looking equation, right? So you can work out the algebraic details, but they are not much. I'm just substituting over here. All right, gamma M minus little delta M. Okay, there's a lot of constants here, and I mean, sure, these constants have an experimental interpretation, and therefore they are very important, but for computational, or if you want, for wanting to derive expressions, they are kind of like annoying. How do we deal with them? Well, we transform our variables. We basically rescale our variables, right? And we've done that several times. In this case, we always can scale two variables, both the main variable of interest here, the concentration of mRNA, and the time variable. So I can rescale time accordingly as I prefer. As a matter of fact, that's a natural thing to do. We could start by rescaling the time, and typically we will rescale time. I'm going to use T prime for the rescaled time units, and I'm defining it just as delta T, right? So this is quite a usual way of working. On the other hand, and I'm writing it here already, this might not be so straightforward, but if you think about it a little bit, notice that if I divide both in this denominator on top of the denominator and the bottom of the, on the numerator and the denominator, I divide by big delta, I see that I'll have 1 plus gamma M divided by delta, and that actually is going to be suggestive, and it's going to suggest to me to perform this scaling transformation. Gamma M divided by delta. Don't worry if you don't get the hang of it at the very first. It's important that you follow this, and if you still are not sure enough to do it on your own, it doesn't matter, because the results are going to be exactly the same. This is just a shortcut to make things maybe more elegant and less susceptible to error as you move onto the derivation. Great, so now we have these transformations, and as I have these transformations, notice that what I'm going to have to do is I'm going to multiply all of these equations by gamma over delta, so that I have a gamma over delta here, and this is going to give me M prime, right, as a variable. And then I have to divide all of this equation by delta, so I get a delta down here, which can go inside the T, right? And as I go inside the T, I have some other delta cancelings here, etc., etc. Now, if you do that, what you're going to be left with, and I'm going to go straight to that, right? So after you introduce these variables in here with the notation that I've introduced, you can use the notation that you want. But the interesting thing is that now this is going to be looking like this. So I encourage you to do this step by step, because it's something that we need to be used to do, right? But the important aspect here is that I'm going to have a simplified equation that is going to be looking like that. Sorry, there's a minus sign here. I'm going to call it this alpha prime. I'm going to explain what these new parameters are. Right? I'm going to have an M prime here, and then 1 plus M prime. That's the beauty of it. There's no more constants. There's only these two constants now. And as a matter of fact, I'm going to just have a minus M prime here for the decay factor, which has now been reduced. Notice that the delta has gone out of dividing the whole equation by delta, as I mentioned before. Great. Nice. What are these new parameters? Well, these new parameters only emerge from this operation that I explained, right? And they are defined as follows. Mu prime, notice this is kind of straightforward as well. Mu prime is going to be gamma over delta times 1 over delta mu, and so alpha prime. Alpha prime is going to be gamma over delta, 1 over delta alpha, right? These are the factors that I multiplied the whole equation by. So that makes sense that this now becomes that. Okay, am I saying this correctly? Yes. Good. So now we can deal with this equation, which is a little bit easier. How do we deal with it? Well, we are, after all, studying its dynamics, so it makes sense that we study its fixed points. So how do we find our fixed points? Well, it is not so clear, because here if we make this equal 0, we don't have the trivial fixed point, namely we don't have m prime equals 0 as a solution, right? This is because there's an independent term here, this coefficient, which to remind ourselves, this is the rate of entry, so therefore there can never be a fixed point where m is exactly 0. That's why the rationale behind this. But we can still make this equals to 0 and work our way out, and if we do so, okay, there's some algebra here that I'm going to be skipping, but we're going to reach, if you notice, when we make this equals to 0, basically what we can have is that mu prime has to be equal to all of these, which carries a denominator of order 1. But we can take out this denominator on both sides of the equation. We have to divide here by 1 plus m prime and multiply on the top by 1 plus m prime, but then on the left-hand side we can bring the denominator to the left-hand side, and all together that's going to give us a second-order equation. So second-order equations carry two solutions, and if you work out the solution step by step, you're going to reach the following. So this is still using the scale of m prime, or the units of m prime, so I'm going to keep that here. This asterisk here is only saying that this is happening for when I am making this. M star equals 0, that's basically the definition of looking for fixed points. We are familiar with this. And let me write here the solution that you should get. You're going to get this term here, plus or minus. Notice that this is actually stemming from a second-order equation. Plus or minus, and here we have mu prime minus alpha prime minus 1 squared plus 4 times mu prime. Imagine that we wouldn't have started by reducing all the variables, right? So introducing all of these rescalings. In this case, this solution, which should be exactly the same if we hadn't done it, it would look very ugly, right? There would be a lot of deltas and gammas in here, which they still are. They are both in the scale, in the units of m prime, and also in the units of mu prime, alpha prime, etc. But this is a little bit more easy to work with, and that's the point of it. Great. So now we have two solutions. There are two fixed points of this system, and we need to think about them to start with a little bit, right? Because these two fixed points, there is one of them that makes no sense. Why? Well, here we had some value, right? Say that this is a positive value. Consider this to be a positive value. This, of course, will depend on the values of mu prime and alpha prime, naturally, but consider this is a positive value. Then if this is subtracted, so from this we subtract, notice the same squared plus something that must be positive. Mu, after all, has to be a positive parameter, as it's defined there. Well, then this is going to be larger than this, and if I were to subtract this, then I'm going to end up with a negative number. And I don't want that, right? It doesn't make any sense to have a negative concentration. So from this argument, we know that m prime minus the solution for the fixed point is going to be negative always, right? If you think about it now, if this were to be negative, well, the worst thing you can do is still add something negative there. So always, for all of the values of mu and alpha, which are both positive values from the definitions over here, then I know that this will happen, so this is a non-physical solution. In other words, we're going to utterly ignore these, and as a matter of fact, I'm going to be renaming the plus one just m prime star, right? Because there's only this solution for our system, this physical solution, this meaningful solution. Okay? So again, now think about it. If we take this term and we add the same squared plus something else, then this is definitely going to be positive, right? And that's what we need to now study a little bit further and explore a tiny bit more. Great. So we know that these are going to be our solution. This is the only solution. This is the only meaningful solution. Because it's positive, as it is greater than 0. Great. Now we're going to be exploring two regimes here, right? And we need to go back and think, what does exactly mu and alpha meant? The first regime that we're going to explore is what I call the mRNA-dominated regime. mRNA dominated. Okay, the mRNA dominated regime, which is basically the regime where mu is much larger than alpha. Let us recall ourselves. So mu was the rate of entry of mRNA molecules into the system, and alpha was the rate of entry of sRNA molecules. So if I am in this regime where mu is much larger than alpha, well, then it makes sense that there's going to be many more mRNAs, and therefore there'll be more expression, right, than if it was the opposite case. And actually, I'm going to call the opposite case sRNA dominated regime, which basically is the opposite. So when the rate of entry of mRNA is much smaller than the rate of entry of sRNA. Okay? So with these two definitions in mind, now I'm going to erase the blackboard, and we're going to go there and explore how this solution, the positive one, which is the one that I need to carry with me, actually looks like. Great, so now we're going to explore these two different regimes, and we're going to start with the mRNA dominated regime. Remember, this means that there's a higher rate of production of mRNA, much higher than the rate of production of sRNA, right? These are reduced variables, but because both are reduced the same way, we are still exploring the same ratio. Okay, so in this case, we see here that this term is dominated by mu. So mu is much larger than alpha. So in other words, we could say that under this approximation here, then this should be something like 1/2, and then here we're going to write mu prime minus 1. We don't know how much small alpha is, so maybe this could be like 0.000001 and then 0.2 over here, and therefore the minus 1 is still significative. So we need to keep it. It's only alpha prime that we can neglect, thanks to the fact that it's being subtracted here from mu prime, which is much larger. Same is going to happen to this term over here, right? So this is going to be approximated by this squared plus 4 mu prime. And then I'll close the brackets here. But notice that this is nothing else but mu prime plus 1 squared, right? Because if you think about it, if you develop this is mu prime squared plus 1 minus 2 times mu prime. But then plus 4 times mu prime, that's going to give altogether mu prime squared plus 1 plus 2 times mu prime, which is nothing else but mu prime plus 1 squared. After I take out the square root that I have here, this is going to give me 1/2. This now is going to make a lot of sense to you guys. Mu minus 1 plus mu prime plus 1, right? Because I've taken out the square root, and remember we're dealing only with the positive solution. Here the minus 1, which we were carrying with us because we were wary of it before, it now cancels away. And as it cancels away, then we have mu prime plus mu prime, which is twice mu prime. Therefore, this is going to be exactly mu prime. Great, so now we want to give back how this looked for our non-primed variables. Therefore, I undo the transformation that I did both on mu prime and in m prime. What you see is that you get that m star, now without the prime, this is nothing but mu over delta. Well, I should write here like this because this is under this approximation. And this makes a lot of sense if you think about it and you argue. You realize that if mu is much dominating alpha, therefore there is going to be almost none of the business regarding the sequestering of the sRNA, right? Because sRNA is produced in such a small amounts, then there's not going to be enough sRNA to sequester mRNA, right? And therefore, from the three terms that we had in the ordinary differential equation before, there's only going to be the first and the latter one, the last term that carried delta m, they're going to matter at this particular regime. That's why when we look at the fixed point, we get nothing but mu over delta. You can think about it a little bit more, but this makes total sense, right? And we're going to call these, actually we're going to name this, we're going to define these as m naught, right? And we're going to use it later on. Great. So we have these, we understand that this had to be a given regime. And now we're going to go to the sRNA dominated regime. This maybe is a little bit more interesting, right? Because now here we are saying that there's a lot of production of sRNA. So there's a lot of production of sRNA, so then what happens? Well, we take the same solution again, right? And now we approximate it, but we need to approximate it using the fact that alpha is much larger than mu. Well, the first thing that we can do without any funny business is just invert these things, because now we're going to be focusing on alpha. So we can maybe take out a minus sign out of this parenthesis here. And so we're going to have alpha prime plus 1 minus mu prime. But remembering that we have a minus sign in front. Alpha prime plus 1 minus mu prime. And then we have all the funny business here that we have to deal with now, which, notice that I can do the same here, but because this is squared, there's no problem. And therefore, I can do it without having to introduce any more signs. Squared plus 4 times mu prime. Great. So far, I've actually done no approximations. But the next thing that we have to do is we have to use the following. I'm going to write it here just as a reminder, that when we have 1 plus something that it's small, right, this can be approximated as 1 plus the same variable, epsilon, plus order square. And we're going to be using this on this square root over here. But this square root doesn't look like 1 plus something small, does it? Well, no. But we could take a common factor, alpha plus 1 minus mu prime, which, by the way, already we can start not caring too much about the mu primes here, which are subtracted from alpha prime. That was the whole idea of changing the sign here. But we could take this as a factor out, which will leave us here with a 1 plus 4 mu prime divided by this factor squared. This factor carries an alpha with it, right? Therefore, this factor will be, by definition, much larger than 4 mu prime, because we are in this regime. So let's do it maybe on the side here. Let's see how I can approximate this. So first off, we're going to drop the mu prime already. So basically, this thing, which I'm going to use an asterisk for, this thing is approximately this thing, right, which is exactly alpha prime plus 1 times the square root of 1 plus 4 divided by alpha prime plus 1 squared. Okay, that's all fine. And now I come down here and I can approximate this still further, but by alpha prime plus 1 times, and now I'm using this expansion, 1 plus 1 over 2, so this 4 is now going to give me a 2. 2 over mu prime alpha prime plus 1 squared. And we're going to ignore higher order terms, right? So notice that I can do this because precisely mu is much smaller than alpha, and at least there's a factor alpha squared here. Great. Perfect. So now we can pull all of this back here, and we're going to get the following. So I'm going to be using it over here, right? So I take all of what I've derived here, and I put it back here. I also ignore mu prime over here, and notice that I get the following. M prime in this sRNA-dominated regime can be approximated by 1/2. I'm doing this step by step, plus alpha prime plus 1, and here I only have 1 plus 2 mu prime alpha prime plus 1 squared, right? I'm doing this step by step this time because I think it's important for all of us to go through these steps at least once. Now, what's nice about this is here I have a minus alpha prime plus 1, but here I have a plus alpha prime plus 1 times 1, therefore these two are going to cancel out. This alpha prime plus 1, it's still multiplying over here, so I will still have it down here, okay? And now, I go up here, okay, and I see that then this, it has to be, remember this is still on the prime units. This will be approximated by mu. Notice that this 2 now here is going to be cancelling with this 2 in front there that we had from the very beginning, from when we obtained the solution. Now this 2 is going to vanish, so we have a mu prime in the numerator, and in the denominator I simply have this. And that's my approximation. So here is where what I obtain, right? Great, that's very, very interesting. I can also say something else here, that this is going to scale like mu over alpha as soon as alpha is much larger than 1, right? So we don't need that for this approximation to occur, but if we still have not only that alpha prime is much larger than mu, but also that alpha prime is much larger than 1, so as we explore alpha, which we will do next, then we know that this is going to scale like 1 over alpha prime. Great. Finally, if we wanted to go to our initial set of units, right? So we have to undo all the transformations that we did. We can see that this is going to give us something like this, right? You notice that here I'm going to have, I'm going to be using also this approximation. So if we are undoing this transformation for alpha prime much larger than 1, what you get is m naught with the definition that I had over there of m naught times delta alpha gamma, which is nothing but m naught over alpha prime. So somehow I cannot really get rid of alpha prime. This is how it should look like. Remember, all of this now is given in the units that we started our problem with. But if you want to be a little bit more elegant, we should use this approach. And why am I writing this now? Because maybe I can do something about it. For example, I could, go out there and plot. And what can I plot? Well, I can plot, for example, the log of alpha prime, which is basically the log of alpha gamma divided by big delta times little delta on the x-axis. And on the y-axis, I can plot the equilibrium value of the mRNA concentration, the true one, so with our initial units, whichever they are, divided by this m naught that I defined over there. And this is what the plot should look like from what we have gathered by studying both regimes, right? So first we had the mRNA-dominated regime. So if here we include the number 1, this is when alpha prime is going to be equal to 1, right? This should collapse, all of this should collapse to this being equal to 1, this being equal to 0, right? Because as we are taking the log here, right, m prime divided by m naught, this is going to give us 1, right? And we know that this is going to happen for the low alpha regime, which is what we have explored over there, right? So basically, this 0 here is not telling us that there's no concentration of mRNA. It's just telling us that the concentration of mRNA here is just exactly m naught. Great. And as we come close to this characteristical value of alpha, then we're going to be changing the regime, and we're going to go somewhere. As we move from 1, alpha is going to start to get bigger than 1, right? And as we get bigger than 1, we get this behavior, like 1 over alpha. And remember, because we're taking logs on both scales, this is going to end up looking like a straight line with slope -1 in this precise units. In fact, units won't matter too much for this straight line, but what matters is the fact that it's sitting here in the denominator under this particular regime. Great. So why is this important? So what have we learned from this? Is there any actual experimental process or maybe an example, a model in biology that works this way? And the answer is yes. Notice that we have established that there's going to be 2 regimes. The mRNA-dominated regime is going to be sitting over here, and the sRNA-dominated regime is going to be sitting over here. And it makes sense because now the free mRNA, the one that is able to be later expressed, right? It's now going down, right? It's going down with this. So this is important because this allows us. It's if you want a tiny example of a switch that can be regulated through the small RNA. And there must be some examples in nature, right? And the answer is yes. I'm going to erase the blackboard and I'm just going to tell you about one of the examples. Great, so we have established already that with our very simplified model, we can already see that there's going to be an mRNA dominated, in which we will have a lot of expression of whatever protein this is encoding for, and an Srna dominated that manages to sequester these mRNA molecules and therefore not allow them to be expressed later on. Right, so these two regimes are now dominated by a few parameters that we can control, and we can actually go out in the nature and measure them. And as a matter of fact, there is many examples that you could find in the literature. There is one maybe famous example, which is the case of these two genetic components. So in E. coli, right, there is this example where you have an Srna, which is called RINB, okay, that it's expressed, all right, and then it's pumped out into the system as Srna, and then there's a morsels in mRNA that can become and be translated then into a protein that basically it regulates the intake of iron in the system, but through the Srna this can be regulated because the RINB is actually binding to the SOTB and impeding its further expression. So this is a type of regulation that it's happening right after transcription. Okay, and we see this example. And if you want to look for more examples in the literature, or if you want to dig deeper into what are the different intricacies of these genes, you can always go to this website, right, where you will find. You can just type down here RINB, and then you'll see a list of all the different explanations that you require, and also references to different papers where they discover these and they discuss all of these different features, right? So in this example, people have gone out and using this method that we have developed here, they've gone out and measured the different parameters, right? And so they have established, if you want, some sort of metrics of how this works. Okay, so this problem still is related. It's going to be related to regulatory dynamics, but in this specific example, we're going to be asking about the idea that we can work with biomolecular switches as if they are precisely this, switches. In other words, they are on or off systems, or systems which they can be expressed as states on or off, either 1 or 0, etc., etc. But instead of just assuming that, we're going to work out an example that allows us to understand precisely how this emerges, right, from a dynamical systems standpoint. Great. So how does this example work? Well, suppose that we have a gene. Here there's the promoter, here's the gene, and this gene expresses a characteristical protein. Okay, this protein then goes into the cell, and what happens is that it can form dimers. So it can bind together with another protein of the same type, right, as in this example over here, and it does so, as we'll say, with some characteristical rate. So in this case, we're going to say that there's a reaction between this protein that is characterized by dimerization and de-dimerization rates, and here we have the dimerized protein, so there's now 2 of such proteins that are being generated by this gene, right, and they can either separate or bind together. Great, but there's some extra feedback characteristic with this dimer, and it's exactly the dimer, only the dimer, that is feeding back into the promoter of this gene, right, and therefore generates more of these proteins itself. So there's this feedback here that expresses the gene further, and it's promoted by the same dimer that it's generated out of the proteins that we have generated with the gene in the first place. So we have now this feedback loop, and we want to explore how this feedback loop is going to be evolve for when we are studying the concentration of protein P in the cell. But we need to go step by step. So we start with this first reaction, and then we're going to enumerate all the other reactions and work them out one by one. So in this first step, we are going to start calling things a little bit different, just to simplify notation. For example, we're going to say that the concentration of protein P is going to be denoted just little p. On the other hand, we're going to say that the concentration of dimer, so that's the two proteins together, we are just going to call it a little s. And now what? Well, now we have this reaction here that we could express in dynamical terms for both P or S, and as a matter of fact, we can do both. So we can write here the derivative of P over time. Well, P can bind together, and then for two P's can go away with rate alpha. So I'm going to have a minus 2 times rate A, sorry, not alpha, but A, P squared, right? But also an S molecule. Remember, this is now double P, but that's an S-type molecule in this notation that I've used for concentrations, can give rise to two proteins P, right, with rate B. So again, we have a plus 2BS. If we instead of having started with this equation, if we had started by studying the equation for S, things would have exactly looked the same, except there wouldn't be no two factors, right? Because we know that P squared is going to generate with rate A is going to generate one element of S, one dimer, okay? But then dimers are going to be de-dimerized. In other words, they're going to be separated, right, at rate B. Right? And so we get exactly, it's very similar equations, right? There's only a factor of 2 between this one, and also a factor of minus 1. This is something that occurs always that, as you're studying this type of equations. And now what we're going to assume here is that these two rates, A and B, are very fast rates. In other words, they're very large values, and therefore, for the purposes of the timescales that we are going to explore this system, this is happening very fast, and this system is equilibrated. So we can say this is fast equilibration, right? So there's fast equilibrium here, and this equilibrium, if you see, this is going to be just saying that this is equal to 0, this is equal to 0, and as I've tried to explain before, this is going to give us exactly the same amount of information. In other words, what we get is that AP squared is going to always be, for the purpose of this exercise, at the time scale that we are exploring this problem, it's always going to be B times S. So in other words, the A times the concentration of the protein, the free protein, squared, is going to be B times the concentration of the dimer. And we shall use this later on. As a matter of fact, we'll use it in a different form. We're going to use S equals A over B divided by P squared. So I'm going to square this, and I'm going to keep it in my memory for later use. So far, so good. We've only explored what really is happening once we have produced a bunch of these proteins, and they're sitting there in the cell, and they're dimerizing, etc. Great. But what else it's important here? Well, I want you to focus the attention on the binding from this dimer into the promoter. How does this work, right? So can we actually depict this somehow? Well, we could, for example, say, all right, so consider this. Consider a situation where I have these dimered proteins here that are already bound into the promoter, and therefore they're going to be expressing this gene. Right? So this is one type of situation that I could encounter in the system. And this is another type of situation that I could encounter in the system, where the gene is just not bound to any of these dimers, and therefore it's just not being expressed. Right? In other words, we're going to say that this is G here is bound, if you want. The gene is bound to this dimer. And we're going to use a different notation. We're going to say that this is like saying GS. Why S? Well, remember, S is how we call this dimer, right? So this is GS, and then we're also going to introduce the following notation, where this is defined as G sub S. So this is the concentrations of genes, or the probability that I have a gene, right, that it's attached to the dimer and therefore being expressed. Great, so we have this distinction now. This, I'm going to say, the gene here is, if you want, free, so it's not bound, but what really this means is that it's not going to be producing anything. We could have called this GF for free, and I want to now make the following definition, which is little g sub f, And that's kind of well, you can argue this is like the concentration of free floating gene without being bound into the dimer, onto the dimer, sorry, or just the probability that a gene, that this gene is not bound to the dimer. So both interpretations are equivalent. Great, so now we have these two variables, but of course, like, there is like, if you want a total number of genes, and therefore we could say that the total concentration of genes in either state, bound or non-bound, it's gonna be G of t. So if you could argue, oh, there's only one such gene, then you could make these probabilities and then let G of t be equal 1. But in this case, we're just gonna consider this to be more general, right? So we have this G of t to be the concentration of all the genes that are sitting there in the cell that are capable of producing this protein. Great, so all of these, why is this important? Well, notice that just as it happened for the dimerization of the protein P, where it comes together and it separates with some given rates, we should be able to argue that the same situation is happening between these two states of the gene. As a matter of fact, you could say that a free gene will pick up, now I'm using S here for double P, all right? But this is, again, this is just the dimer as we have stated before. And we could have these two rates. Either I bind, right, and therefore I become a gene that is bound here, and I can access now the process of generating new proteins, or I can unbind, and therefore I go back to this configuration over here. Oh, so this is again looking like some equilibration process that needs to take place. And we need to develop these. And we also are going to argue that this is happening at a faster rate than the rate at which any of the gene is going to be expressed and then translated into protein. Right? So this is still a fast timescale compared to the timescale of generating new proteins. Therefore, we can still argue that there's going to be fast equilibration. And if there's fast equilibration, I can use these constants here that I invoked in order to get some relation between these variables, G of S, G sub S, G sub F, and the total number of genes is T. Great. Let's bear in mind that, of course, this has to hold, as I mentioned before. And now, thanks to this fast equilibration, what we can say is that K plus, that's this probability over here, K plus times GF, because here we have a GF, times S, it's going to be equal to K minus, that's this way for the reaction, times J sub S. Careful here, this is a sub-index. But we can do more, right? Because we know that thanks to this, right, we can include this relation over here and rewrite this as follows. So here I'm going to substitute G sub F by G sub T minus G sub S. So I'm going to do this step just to be clear. Only thing I've done here is I've substituted G sub F for G sub T minus G sub S. This is times S, and I have K minus G sub S. Because throughout all the problem, this has to be a constant value, right? Because we are not generating or eliminating any of these genes in the cell, then this is a constant. And in this equation here that comes out of this fast equilibration for this reaction, then there's only one single variable that could interest us, which is G sub S. So we can just get it out from here and obtain it by resolving this equation, which gives us the following. There's going to be a denominator here, and there's going to be K minus plus S, and then in the numerator there's going to be K plus GT, which is again a constant, times S. So now we have this expression here. And there's only one last thing that we need to bear in mind now, and it's maybe the most important thing, the most important aspect, that we probably would have wanted to jumpstart trying to solve it, but if we would have done that, then we would have committed the mistake of omitting all of these aspects before, which are the two equilibration processes that are happening underneath the main process of generating new protein, right? If we want to generate new protein, what we should look at is this reaction. So we have the gene which is bound to the promoter, right? And then to the dimer that is bound to the promoter, and that is giving rise with a one-directional reaction, and some constant rate, k sub c here, it's giving rise to the gene, then the dimer unbound, right? And then the protein. And this is the important part here. This is what we want to remark, that now we are generating protein. There's also going to be some protein decay, which is going to give rise to another time scale here, delta. Okay, and these two reactions, I'm going to call this reaction 1 in Roman numerals, and then this reaction 2 in Roman numerals. These two reactions are happening at the time scale that we are exploring the system with. In other words, we see how this is raising or lowering using the time scale that it's dominated by these two reactions. The other reactions are happening very fast, so they are equilibrating very fast, but they give rise to these non-trivial expressions that they're going to appear now. So in other words, I want to explore this, but in the time scale that I've just said, which is different from the two time scales before. And just looking at these, I see that there's going to be two contributions. Right, so the contribution from the first reaction, the contribution from the second reaction. And the first reaction is rather simple, so it's just Kc times the concentration or the probability of genes being bound to the dimer and therefore being expressed. Right, that's G sub s. And then minus delta P, because this is being also decaying. Great, perfect. We can now take all of the information that we got, some from here. Remember, we had that S was A over B times P squared. Where is this S coming back? Well, it's coming back here, where we have G sub S in terms of all constants and S. So we need to pool all of this information back here. And we do so, I'm going to do it right here, and we get the following. I'm going to write it in a very interesting way. I'm doing some algebra here, but I want you folks to do it at home as well. Okay, I get all of these different constants. I'm going to put parentheses here. Then I get P squared. And then in the denominator, I get 1 plus A over B K minus P squared minus delta P. There's a step that I skipped here, which is, remember here we have G sub S, and G sub S in the denominator has K minus plus S. But here we don't see K minus plus S, we see 1 plus all of this. Well, this is S, if you recall, but K minus it's dividing, and this is because I divided on both sides, so on the numerator and the denominator I divide by 1 over K minus. Why did I do this? Because there's so many constants here. I don't like dealing with this many amount of constants. So I need to come up with some clever way that all of these constants are going to disappear. Or not disappear, but we're going to be hiding them under the rock. And the way to do this, we've done this before already, it's I'm going to call P, I'm going to use P prime for this redefinition of the units of P. And remember, this is the amount or the concentration of protein. And I'm going to be calling it the square root of A divided by B K minus. Well, notice that this is just something that I'm pulling out here from the denominator because I have A divided by B K minus, but I have a P squared here, so if I want this to be just a pure variable squared, I need to call this a square root and then put it inside. And that's why I get the inspiration, where I get the inspiration to actually write this down, right? I mean, this way of writing P and this way of writing P, I know this can create some confusion, but it's exactly the same P. Is now, this is primed. The time, on the other hand, doesn't surprise us at all because we've been doing this also several times, which is I am going to use the decay rate here to imbue the time with some units. So in other words, we are just going to call T prime delta T, right? So that's giving units of time in terms of the decay rate. Now if you do this, then this equation becomes the following, and I'm going to do it right here. Remember, you need to now multiply on numerator and denominator by these fellas, the prefactor of P and then the prefactor of T in the denominator of the equation, work it out, put things together, and you'll see that you get the following. Alpha, and now you will see that this actually looks much better. Right, so alpha p prime squared divided by 1 plus p prime squared minus p prime. And the interesting thing is that now we only have one single parameter. Okay, this parameter actually carries a lot of information. We shall write it down. Alpha here is defined as k sub c, k sub plus divided by delta square root of k sub minus g t and the square root of a over b. So yes, all of these constants are sitting in this alpha, but from the dynamical systems standpoint, this is way more treatable than if we were to be dealing with all of these constants all along. As a matter of fact, this very simple way, and we've repeated this sometimes already, but this very simple way of reducing all of our equations actually allows us to see what's really important for the dynamics of the system. And the important conglomerate of constants is this one. This is what really is regulating, is going to be regulating the dynamics of the system, as we shall see next, okay? Great. So now we have proved this using the assumptions that we had in hand, namely that the binding reaction for the protein into dimers was a rather fast one, and so was the reaction from the dimer to the promoter of the gene, right? So it bounded and unbounded, it binds and unbinds very quickly. Both of these binds and unbinds very quickly, and now the time scale that we are looking at the system with is the time scale of protein production and decay. This left us with this very simple equation, although there was a lot of work that had to be done with all the different constants that were playing a role here, and they are all collapsed into this single constant, alpha. Now that's something very important here. It's a remarkable lesson, which is, well, interestingly, we got something that might ring a bell for many of you. Well, because we've seen this before, because this is nothing but a Hill function of order 2. Right? So sometimes when we're studying regulation, we just invoke functions here saying, oh, well, then the derivative of this protein will be the Hill function of order 2, and so on. But where is this denominator with a squared value comes from? Well, now you understand how this comes from. It comes from actually having integrated other rapid equilibration processes that are happening underneath the time scale that we're looking at the problem with. Okay? Now with all of this information we can move on to our favorite toolkit, which is solving fixed points and studying the stability of those fixed points. Very quickly, by a simple look at this equation, if we want to study fixed points here, so we basically are going to consider points p prime star such that this equals 0, and rather quickly we see that these fixed points, there's going to be in total 3 candidates for them. The trivial one is sitting here, right? So if I make p prime equals 0, well, this is a fixed point, and we'll see a little bit more on this fixed point later on. I'm going to write another fixed point here, which is actually going to give rise to 2 fixed points, and I'm going to explain very shortly how you do this, but I expect you to do it yourselves because it's a rather simple exercise, right? So notice that there's going to be another fixed point stemming from the fact that if I let this equal 0, and I assume that p prime is not the trivial fixed point, then I have this equation equals 0, but it has a common factor p prime, which I can cancel out, and I'm going to be left with something like this. So this other fixed point, which are going to be actually 2 of them, right, is the solution of the following equation, alpha p prime star divided by 1 plus p prime star squared equals 1. Notice here, I've already cancelled this p prime here that went into the other side of the equality here. Great. This actually, as I pull this onto the right-hand side, this gives rise to a second-order equation, which we can solve. And we can write down the solution straightforwardly down here. And notice that because this is a second order equation, this gives rise to two different fixed points, right? Which I call P prime plus minus, with a star up here, noticing that this is a fixed point. As a matter of fact, this is the solution of this simple degree 2 equation. And there's a lot of information coming here. There's a lot of information coming here. Because to start with, we know that P stands for the concentration of the protein in the cell. So it can never be negative, and worst off, it can never be a complex number, right? So first off, are both of these solutions sensible solutions? The answer is yes, because alpha divided by 2 plus something that is smaller than alpha divided by 2, because it carries a minus 1 here, that's going to be a positive value. But alpha divided by 2 minus something that is smaller than alpha divided by 2, it's also going to be a positive value, except when alpha is a bit weird, right? But we'll talk about this now. Therefore, both solutions can be suitable. However, if alpha, that's what I was hinting at before, if alpha is smaller than 2, notice, if alpha is smaller than 2, this is going to give me, smaller than 2, this is going to give me something that is smaller than 1, which is squared is still smaller than 1. When I subtract 1 to that, I get a negative value in the discriminant of this square root. Therefore, for alpha smaller than an alpha critical, and I'm going to call this critical alpha up here, just 2, the value 2, when alpha is smaller than alpha critical, then P plus minus, these fixed points, they don't belong to the reals. Okay? They are complex numbers. Therefore, we cannot consider them as feasible for our problem. However, when alpha is larger than alpha critical, we do get real values for both. Okay? And these are the ones that we want to be looking at. And of course, if we now consider alpha equals alpha critical, which is, again, the value 2, this is going to give us 1 minus 1, which basically cancels the discriminant and cancels the square root, and gives us that P plus equals P minus, okay, and equals exactly alpha halves. But because alpha is alpha critical, that's 1, okay? Remember, this sounds a bit strange because 1 means it's full of proteins, right? Well, no. We have to remember that we have changed the scales, the unit scales that we are looking at for this P. Remember that we've done that before in order to obtain this simple equation. So this 1 is not indicating now that the system is full, not at all. It's just indicating that we have to multiply our rescaling factors for the concentration of the protein by 1 in this case. Okay, so let's bear that in mind. We still will be plotting everything on the prime, P prime sort of unit scales. Okay? Okay, so now we have these 3 features for the 2 fixed points that we obtain from this side. But, so in general we have 3 fixed points here. Okay, and with this information also, we could just go on here and plot them. Right, so here I'm going to say, okay, this is all the fixed points that I see, and here I move alpha, which is naturally only a positive. Here I'm going to write alpha critical, and this is alpha. Remember, this is exactly 2, with all the rescalings that we had before from the previous constants. Remember that. This alpha contains a lot of information. Great. Now I'm going to just plot the 3 different fixed points. I'm going to use colors. This one. All right, so there's going to be the trivial fixed point, which is 0 all along. Right? And we're going to call this the trivial fixed point. So if you want, this is P naught star. Okay, and then we know that for alpha below alpha, critical alpha, there is no possibility of having the other 2 fixed points existing, right? Remember that we had this condition over here. Therefore, we can just ignore what's going to happen for the other 2 fixed points for values below 2 for alpha. However, at exactly alpha equals 2, in the units of, in the primed units, this is going to give us p prime equals 1. And there's going to be two solutions, two branches of this square root that are coming on both sides, right? So there's going to be the upper branch and the lower branch. So the lower branch, I'm going to paint it like this. And the upper branch, I'm going to paint it like this. Okay, great. So this, if you want, is going to be P1 plus, okay, and this is going to be P1 minus, okay? Great. So we now have how this bifurcation diagram should look like. And we want to interpret this. But first off, we need to look at, well, okay, who is stable here? Now remember that the trick when we have many different fixed points, and we are in a one-dimensional system, in other words, one system of one single variable, is to look at the trivial fixed point. Because in the trivial fixed point, if I study the lambda coefficient, we see, and I let you do this at home, that if you take the derivative of the right-hand side of the ordinary differential equation and you equal to 0, the only thing that you're left with is a minus 1. This minus 1 is stemming from this part here, that if you remember comes from the decay rate, right? And this is always less than 0. Therefore, the trivial fixed point, it's always stable. Great. The trivial fixed point is always stable. What happens to the other fixed points? Well, now we can use the fact that we are working with one single variable, and the topology of the dynamical system only allows for the stability of the different points to be consecutive. In other words, if I start drawing what happens for alpha smaller than alpha critical, what I see here is that I have the 0 to be a trivial fixed point, and there's no other fixed points, right? So there's only this attractor. Great. This means that here I'm going to have, right? I'm going to have this to be a fixed point. But not only here. As a matter of fact, this happens for all possible values of alpha. So if I continue on here, this is all a fixed point, a stable fixed point. So anything that comes along this side over here and all the side over here is going to flow down to 0. What's happening at alpha larger than alpha critical? The 0 still is a fixed point. But now we have another fixed point and another fixed point corresponding to the two branches, right? It's as if I am reading this on this direction exactly, right? Because this is nothing but the p axis, the p prime axis. But I cannot have a stable fixed point and then another stable fixed point. In this topology, I can only have this as an unstable fixed point, right? So this is going to flow like this, and then this one needs now to be a stable fixed point. And hence, I have finished the exercise without having to compute everything that was going on for the non-trivial fixed points, right? Interestingly, if you want to be also more succinct to what happens to the critical point, I allow you I would like you to think about it. But here you have an inflection point. It's not exactly an attractor, because what happens here is you flow this way, but here you also flow that way, right? So this is a particular fixed inflection point that it happens just at the critical value. So this, we can draw it like that with a semi-filled circle. And we're almost done here, right? So basically, this is a repulsor, as we've said. This is the one here. So this is the one here, okay? And then finally, this is an attractor, right? And of course, if you go up there as well. And now we have the full picture of how this should work and where the transition from not being active to having the possibility to be active is sitting at. It's exactly sitting at here. And now let's interpret this a little bit further to finish off with this exercise. So if I were able to manipulate somehow through enzymes or through some biomolecule the parameter alpha in my system, I could maybe push the system from this state here where there's going to be no protein expressed because all the system will flow to 0. And then if I move alpha towards this side, well, if I'm sitting at protein level equals 0, then things look like they're still around 0 here. But a little bit of a fluctuation can kick me up from this lower branch. And as soon as I reach here, I'm going to jump up there, right? And therefore, here, if any little fluctuation is going to push me up to this high level of expression, which we can consider to be the on level, right? And therefore, this is giving rise to, if you want, a binary expression for P, the concentration of protein, out of very simple chemistry that we have worked out step by step. And that's one way of understanding how we can actually talk about regulation in terms of binary variables.